Unit tests are tedious to maintain, so much so that I just didn't write them at all, until I started doing snapshot testing. I broke down the process into 3 distinct parts, and these are my problems with them. We have creating unit tests, verifying their output, and debugging what went wrong if the test fails. Say you have function get that returns a complex type. When we create a unit test, we call the function with some input and then we initialize the output. This part right here, initializing the output, I find that to be boilerplate code. Ideally, what happens is you let the program automate this output field here when you run the tests, and then you just look to verify if it's correct. That brings us to our second part, verification. Verifying that the output that you initialize is actually correct based on some given input is hard once you have much more complex structs that you're initializing, especially when they're large structs and you're just looking at this big gulf of source code. You can alleviate this problem by having a human-readable string representation of the type, but this goes back to the problem of creating unit tests. When you change the formatting or your type stringifies to large text, changing the string representation or updating the internals adds a lot of friction to updating your unit tests because everything will start breaking again, right? Moving on to debugging. Once your test fails, the ease of you figuring out what went wrong is dependent on the error message that you wrote at the time of creating the unit test. Now, creating a good error message has always been a subjective topic. Ideally, we just eliminate this decision altogether. How do we do that? Well, we already have this human-readable string representation of the type, hopefully. And this was created so that it's easy for us to verify that the output is correct. So let's just take advantage of this string representation and use that for debugging. In other words, when a test fails, let's just compare what the string representation is of the actual output and what we were expecting to get. This brings us to snapshot testing. We'll discuss what it is, what it does, how to implement it. We'll also discuss Myers Diff in detail, and all of this will be implemented in Golang. Quick side note, all of my videos are unmonetized and will remain so. I do not earn any revenue from ads you may see. This is the video outline for your convenience. We have the introduction, the body, starting with snapshot testing, Myers Diff, and then the conclusion. Timestamps are available in the description below. This terminal icon indicates that there's a coding segment after the current slide. You'll see it in the top right corner of the slide. The objective is to streamline unit test maintenance in aspects of creating, verifying, and debugging the unit tests. Snapshot testing. Snapshot testing is a technique for the assert part of an arrange act assert test that dispenses with handwritten assertions and instead uses comparison to a known good value, a snapshot. This comes from TigerBeetle's blog right here, written by Matt Cladd. Enter full screen. And this is quite a mouthful and hard to understand, so I'll simplify it in my own words. Snapshot testing is the automated serialization of a unit test's output, what we call the snapshot, and assertion that subsequent test runs reproduce said output. Let's take a look at 2 examples, a basic unit test and a batch of unit tests. Go see, sh, go. Package sh is a package that I created to emulate shell scripting in Go. so that you can avoid bash scripting altogether. And we'll focus on this function right here, push dir, which is a direct equivalent to push d, which is just a change directory, but then you can also do pop d to go back to where you previously were. Yeah. Let's look at the unit tests. And what we're doing here is we go back to parent directories, and then we assert the directory that we are in. So if you look at the file path here at the bottom, we start at package sh, the parent is experimental, and then the next parent after that is Golang snacks, the project root. Let's zoom out a bit so we can get the directory before Golang snacks as well. And if we run the test, no, not Myers, sh, and let's do count 1 so there's no cache. Oh, that's wrong. Experimental. It passes. Now let's change the directory. Let's go up one more level, and if we run the test again, it fails. We were expecting Golang snacks, and now we got code. We can change init to be edit. Save the file, and now when we run the tests, it passes, and when we go back to the source code, it gets updated. We can go back one step further. You'll see here, and immediately let's go edit here. If I run the code again, it passes and it gets populated with the next directory after that, which is my home directory. Let's go back. Yeah. Now let's look at a batch of unit tests. Where is it? It's in Myers, yes. And we'll look at this test find common suffix, which finds the common suffix between two slice runes. The idea is simple. We have a bunch of inputs that we need to try. First, we create. Oh, I'm sorry. This is very disorienting. We have a bunch of inputs that we need to try. We start by creating an entry struct for the test name and whatever input parameters we have, and then the snapshot where the output gets populated. We create a slice of these entries, and then we loop over them. Now we have a check function that asserts the snapshot. Let's run this code. Go test Myers count 1 to avoid caching. It passes. Here's what I want you to notice about this setup. Let's say we have a test case here that has an incorrect output. Let's run the test. It fails. Here we go. Expected arst, we got none. If I change this to edit, it still gets updated. So the place where you initialize the snapshot does not need to be in the same place as where you assert it, which allows us to abstract over these batch of unit tests and just have one simple check function that iterates over them, and then we can aggregate all of these snapshots into one slice. In other words, it makes it more readable when you have all of these snapshots together and you can assert them in some place else. Another thing to note is if we change the format of the string here, string actual, it's very easy to update all of them. So, and to just to show you, it'll fail, and all of them will fail because now they all have meow appended to them. Let's select all of these test cases, replace init with edit, and run the test again, and they get updated. Okay, nice. So this was inspired by TigerBeetle, their blog called Snapshot Testing for the Masses. It was created by Matt. He's the creator of Rust Analyzer, and now he's working at TigerBeetle. And that's the blog that I showed earlier. And the implementation is simple. There's two parts to it: generation of the snapshot and asserting that the snapshot is correct. So you track a snapshot source location, then you replace the snapshot string in the source code. So technically this is basically a meta programming, but like the lightest version of meta programming. And then you also need to handle multiple edits in the same file. The one where I did, I highlighted all of these entries, and then I updated them. So that'll happen all in one process. So you need to handle concurrent access to a single file. And then assertion, you need to assert the input string against the snapshot and then print the mismatches. Okay, so let's go take a look at the implementation. Snap.go. So you have your type here. Okay, let me zoom in. You have your type snapshot, which takes in your expected string, the one that gets populated in the source code itself, the file path and the line where it exists, and a should edit field, which indicates whether you need to update it in the source code. One thing to note here is that you can only have one snapshot call per line in the source code, which is easy enough to do. You won't have to think about it, but it is critical to the implementation. So just bear that in mind. Next, we have the init and edit functions that initialize a snapshot based on some given data string. Now, it's critical that the argument to these functions are string literals and not variables, because we'll be replacing them in the source code directly. If you allow variables to be passed as arguments here, then you need to do static analysis on the program so you can resolve what string literal these variables are pointing to. So just make it so that the caller always needs to pass in a string literal. In this case, you always need to pass in a string literal with backticks. So you cannot do double quotes. And this simplifies it so that we literally just have to insert the string inside the text, and we don't have to think about escaping and whatnot. Okay. The difference between these two functions is that with edit, we enable the should edit field. The way we get the source location is during runtime, we inspect the stack trace and look at the file name and line number of the call site. Now, because of this is going to be brittle under Go generate if you're doing other meta programming stuff under your test run. So just bear that in mind. This assumes that the source code won't change from what it looks like during compile time. Okay. Another thing to note here is that both of these function identifiers have the same length, which simplifies how we insert the string into the source code, because now we're only taking into account the difference between the two outputs instead of having to offset the file by whatever the difference is between these two identifiers. In the blog, instead of edit, they have it as update, and so you need to take into account these extra two character offsets between the two identifiers. Next, you have a global map that tracks all of the file modifications that you've made throughout the test run, and this is protected by a single mutex. Now you can have it so that each file would have their own mutex, but in practice it's not necessary because most of the time you're just updating one file anyway. Now we have the is_equal function, which is the bread and butter of this package. And just to show you, this is not a huge package at all. It's just 200 lines of code. And if you look at the API, there's just three functions here: init, edit, and is_equal. That's as far as I'll go in terms of explaining the implementation. if you want to understand how exactly the string is replaced in the source code, you can just read the library. I'll have it in the description below. The function is just 117 lines of code, and a large chunk of it is just assertions, so it's very easy to read. And if you look at how many assertions this is, there's 16 assertions here. Takeaways. Number 1, snapshot tests are ideal when only the end result matters. They remove the need to handcraft expected outputs by letting the code generate them directly. And part 2 of this is structural assertions still require helpers that inspect the object itself. To illustrate, let's go to my Myers package. Myers. We have here a type differ that has a size of edits based on some input string. And I assert here here we go. I have an assertion here that you must be able to rebuild the input strings from the slice edits. And you can't do this with just the string representation, or at least it's going to be much more complex, because now you need to parse the string representation of the diff and then rebuild the size from that and then compare the size. So here we just directly inspect the object itself. I asserted this instead of a unit test, but the idea is still the same. This isn't a use case that snapshot testing can cover. Takeaway number 2, creating human readable representations of data is incentivized to ease verification of outputs. This incidentally improves quick printf debug sessions. This is what I said earlier about foregoing creating good error messages by taking advantage of human readable representations of the type itself. Takeaway number 3, the simplicity value ratio of snapshot testing makes it one of the most valuable patterns to adopt in your code base immediately. Given that it's only 190 lines of code, it drastically changes the testing practices in your organization and you as an individual. Now, there's still a glaring deficiency in this implementation, particularly in the debugging experience. Go back to GoC, and it's the fact that when there's a snapshot mismatch, we are printing out the string of the actual output and the expected output as is, side by side. And you can imagine that if there's a large amount of text, it's going to be hard to figure out what the differences actually are. To illustrate, let's go to my logger package and find a unit test with a lot of text here. Okay. And it says, okay. Let's say you made a typo while you were scrolling this buffer, and you accidentally made this period into a space. Now, this is going to be hard to detect with the naked eye, and when you run the unit test, it'll start failing. Epilogue. There you go. Now, here, this is what I was talking about. When you have a large amount of text, it's hard to figure out what the actual differences are. Now, I'll change the snap package here to use the one where it has a Myers Diff implementation. And when we run the test again, go test Epilogue, now it highlights what the actual differences between the output is. Okay, so this is implemented in native Go. It's not executing an external process to display these diffs. I implemented Myers Diff itself, and this is a much better debugging experience. Okay. Now, before we start discussing about Myers Diff, I'll first drink some water. You go stay hydrated. Okay. Myers Diff. Diff algorithms produce a sequence of edits that transform one sequence into another. Myers Diff is a general-purpose diff algorithm producing the least amount of edits required. Version control systems use it for this exact reason. Other domains prioritize efficiency or semantic grouping, which require different algorithms. And these definitions are of my own words. They're not from some official source like Wikipedia or whatever. And I'll show you two examples, character-based diffs and line-based diffs. Go back to GoC. It's in the Myers package, the unit tests. Starting with character-based diffs, we have two strings here, the dog in the hat and the cat in the hat. This is the previous string and we want to turn it into the second one. The resulting diff is that it changes the word dog into cat on a character by character basis, subtracting the letter D, then the letter O, then the letter G, C, then adding C, A, T. And it retains the common suffix and common prefix of the two strings. Line-based diffs, you've already seen it earlier with where is it? With this one. So it highlights the conflicts on a line basis between two strings. These are the resources that I used to learn this algorithm, starting with the original academic paper by Eugene Myers, an O of ND difference algorithm and its variations from 1986. And honestly, I tried reading this paper and in my opinion, you don't need to read this. It's focused on mathematically proving that the algorithm will give you the least amount of edits. So, I mean, if you're interested in that, then go ahead and read it, but it's quite hard to read, especially if you don't have a mathematics background. And what's important is that you understand the idea of the algorithm and that you can visualize how it creates the diffs. So, with that in mind, there's two resources that do exactly that. The second resource is James Coglan's, I don't know how you pronounce this, Coglan. James Coglan's blog series. He authored the book Building Git, and he has a blog on the Myers Diff algorithm itself. So here he discusses the idea behind Myers Diff, and I'll be explaining it myself because I think it's still quite hard to understand just from reading the blog, and you really need someone to visualize it for you. The last resource is Neil Fraser's blog. He's a former Google engineer, software engineer, and he maintained Google diff-match-patch, which is now a publicly archived repository. He wrote a blog discussing the optimizations you can make on the algorithm. This was written back in 2006. These optimizations are based on simple heuristics, for example, figuring out the common suffix and prefix of the two strings so that you can apply the diff algorithm on the middle part instead. And there's a bunch of other heuristics here. And these optimizations are not only focused on improving the efficiency of the algorithm, but also the semantic semantic aligning of the diffs, or in other words, how easy is it to read. For example, there's this diff here at the end. Take a look at these three diffs. These are all the same diffs in that they result in the same string. But you can obviously tell that the last diff here is much easier to read compared to the first two diffs. So what's the theory behind Myers Diff? There's two things to keep in mind. Is that it's a shortest path algorithm and it computes this through a breadth first search. But honestly, it's more like a breadth first search in combination with depth first search. And I'll visualize it with my whiteboard here. Full screen my face. Yeah. First, it visualizes the problem as a path algorithm. So I have two words here, meow and Bert. We want to transform the word meow into Bert. You have three directions of movement: rightwards, downwards, and diagonal. When you go to the right, you are deleting a letter from the original word. When you go downwards, you're adding a letter from the new string. And if we go diagonal, that means you are retaining a letter from the old string. So, thinking about how we can transform this, there's multiple ways. So starting at here, we see that M and B don't match. So let's delete the letter M from meow. And I'll have here the final output so you can visualize what's happening. So we delete the word M. Okay. Is E and B matching? Nope. So now we add the letter B. This becomes B. Now let's check, is E and E equal? Yup, so we retain that. Now we check, is O and R equal? Nope. So now let's say we add R instead. So we insert an R in between, bare row. Yup. And we check, is T and O the same? Nope. So let's delete O, T, W, and you get the idea. This becomes T. So that's just one path available in this problem. You can also just do this. You can also do this. You can also do this. There's a lot of ways to reach the final word. And what Myers Diff does is that it finds the most numbers of retain that you can do to minimize deletions and additions, because it's cheaper to do a retain than to do deletes and adds, because a delete and an add is 2 operations while a retain is simply 1. It's a combination of breadth first search and depth first search. Breadth first search in that it compares the first letter and then the second letter, third letter, fourth letter. It's depth first search in that if it finds a letter that both words share, it'll try to extend that retain snake until it reaches the end, hopefully. So let's say you do a delete, then insert, delete, insert. You find that A is shared by both strings. So now you retain this, and instead of checking other paths from this point, you immediately try to check at this point whether A and A is equal. So it is equal, so you extend the snake, and lo and behold, you reach the end. You've completely transformed the string. Now you didn't have to, you completely skipped comparing the last letters with each other because the snake started from the third letter. Hopefully that makes sense. Implementing Myers Diff can be broken down into 2 phases: search and construction. First, you search for any path that leads to the final transformation. And then you construct the shortest path based on all the paths that you tried prior to reaching that final transformation. Under search, you track the furthest x reached for each diagonal and depth. You also prioritize deletions over insertions. This is to improve semantic aligning. What this does is now you're grouping deletions together and insertions together as much as possible. Bring it back to the blog that I showed earlier in Neil Fraser, where you have 3 diffs that lead to the same output or to the same final string, but one is much more readable than the other because the deletions and insertions are grouped together. For line diffs, map each unique line to a rune, then character diff that instead. Construction, we rebuild the path by iterating the furthest x trace in reverse. So we just do the completely the same thing we did in the first phase, but we're iterating over the furthest x that we tracked, but in reverse. Let's visualize the implementation first. So I have this. This is the example from James Coglan's blog. Actually, I'll show it first. James Coglan. Yeah, in part 2, this is the example that he used. Okay. And I'll show how to do this later, but there's a couple of things that you need to understand first. What did I do here? Well, I did what the algorithm would have done manually, and I skipped a little bit on the final part here, and I directly went to the final transformation because I couldn't be bothered to do the whole thing. So since this is a path algorithm, you can imagine this as a grid, a Cartesian plane. I don't remember the term, a Cartesian plane where you have coordinates. So this would be x, the x-axis. This would be the y-axis. Now, even though this is going downwards, we count the we increment the y-axis in the positive direction, the positive infinity. So this would be this would have a y value of 1, 2, 3, 4, 5. It's not -0, -1, -2. Okay. We did that because if we actually try to follow the proper orientation, then this word would be read upwards, and that's just not a thing, right? You read it downwards. Okay. Then you also have k. I hope you can see that, k. So k represents the diagonal of the point. Okay. So let's take this. Let's take the very first point, for example. This has an x and y of 0, 0, and the diagonal would be 0. X 0 minus 0 is 0. So a diagonal of 0 means the very middle diagonal of the two strings. Okay. We can visualize it with this. This would be the 0 diagonal, right? Now let's take another arbitrary point here. Let's take this, for example. This has an x value of 1, and the y value is 0, 1, 2, 3. Okay, so this is 0.13. Now what would be the diagonal here? Well, 1 minus 3, I just burped, is -2. And if we count, this is the 0 diagonal. This is the 1 diagonal, -1 diagonal, right here. And this is the -2 diagonal right here. Yeah? So this is part of the -2 diagonal. This one. This is part of the -2 diagonal. And to visualize it better, you can turn the grid diagonally. This is actually what James Coglan tried to do in his blog, which is hard to do if you're doing it in a text-based material. Yeah, he actually said to think about it diagonally. Yeah. So the middlemost diagonal would be 0. This is -1. This is -2, and then this would be negative. This would be +1, +2, +3, +4. Okay. Hopefully that makes sense. We track the diagonal here because this is what will determine whether we prefer a deletion over an insertion, because even though I said to prioritize deletions, there would be a time where you would prefer the insertion. Manually solving for Myers Diff, there's 2 steps that you need to follow for each point. Number 1, you choose whether a point originates from an insertion or a deletion. So, for example, these are the previous paths, and now we're evaluating this point. Now you need to choose whether it comes from a deletion or an insertion. Oh, that is horrendously drawn. Okay, whether it comes from a deletion or an insertion. Okay. I said earlier that you should prioritize deletions, but there are cases where you would choose an insertion. Number 2, ask yourself whether it creates a snake. So a snake is a chain of letters that are shared between the two words. So for example, let's say we're in this point right here, and the two words create share AB and AB, so it would create a snake here in the middle. Okay. Now let's put it into practice, starting with the origin. Here. Now we choose, does it come from an insertion or a deletion? Well, it's a start, so there's nothing to choose from. Move on to the next depth. And we start with the leftmost point. It doesn't really matter where you go, where you start, as long as you go through all of the points in each depth. So there's only one place that this point can originate from, the origin. Technically, this would be a deletion if you were to extend it past the grid, right? Okay. Does it create a snake? Is B equal to A? It's not. So we move on to the next point. There's only one place it can originate from. Is B equal to C? Nope. So it doesn't create a snake. That's all of the points for this depth. Now we move on to depth number 2. Okay. Now I'm plotting all of the points for this depth. Okay. Starting with the leftmost. Is A equal to A? Yup. So it creates a snake. There you go. Oh, let me try to find. There you go. Now we try to extend the snake again. Is B equal to B? Yup. So, oh wait. Yeah. Is B equal to B? Yes. So we extend the snake one more. There you go. Is A equal to C? Nope. So that's the extent of it. Moving on to the next point. Now we actually need to choose whether this point originates from a deletion or an insertion. The deciding factor here would be which one of the two reached the furthest X. So, for example, the point to the left of this created a snake and it reached all the way here. Then we would connect with this point. Yeah, that's when it would take priority over the deletion. Now let's say it only created a snake up until to the second X to X number 2. There you go. And then the point above the deletion reached a further X. Then we would connect with the deletion. Okay. Now here, there's no snakes, so it's much simpler. The X of the point above is 1, while this guy has an X of 0. So we would connect with this guy. We would prioritize we would choose the deletion. Okay. Then you go on to the next point. Same idea. There's only one place for it to originate from, so we connect. Is C equal to C? Yep. So it creates a snake. Is A equal to B? Nope. So that's the extent of the snake. And then you just do that for all depths. So you do this. Continue here, 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 and then you check this. Does it create? Yep, it creates a snake. Oh no, it doesn't create a snake actually. Yeah. So that's that, and then this you prefer the deletion. It doesn't create a snake. This you prefer the deletion. Does it create a snake? Nope. There you go. And then you just do that. Continue on with the other depths. Now, one thing you may have noticed is that the two strings differ in length. So what happens when you reach the wait, which one's shorter? Okay, this one is shorter. Okay, so what happens when you reach the end of this? Well, you just start your points here, and then you match it up to the characters there, and then you do this. Hopefully you're imagining what I'm doing here. Yeah. So it doesn't have to be always like the leftmost point. Like, it doesn't have to be stuck to the wall. You can, a depth can start in any axis. Okay? So you're iterating over these points with each iteration until you end up to the final transformation. So this is what it would look like. Yeah, as you iterate over it. And that's the idea behind it all. When reconstructing the path, we do the exact same thing, but in reverse. So you start at the final transformation. So the location of this, the coordinates of this point would be 0, 1, 2, 3, 4, 5, 6, 7, 7, and then this would be 1, 2, 3, 4, 5, 6. Okay, so its coordinates is 7, 6, and the diagonal would be 7 minus 6. It's on the 1, k is equal to 1. So if we draw a diagonal from the origin, it will lie here. This would be the final transformation. Next, you reference the 2D array that was used to track the furthest x reached by each diagonal for each depth. Assuming this is depth 0, this would contain zeros only. All diagonals reached an x value of 0. Then for depth number 1, assuming that the middle element is depth diagonal 0, and then to the left of it would be the negative diagonals, and to the right would be the positive diagonals. With the depth 1, origin is the middle diagonal would still be 0. K negative 1 would still have a furthest x of 0, but K1, this guy, now would have a furthest x of 1. Then you use K as an index into this array to figure out at what point was at what x column was this point reached. So imagine that this is the final transformation point. Was it reached by x6, x5, x4, x3? So we're looking for how long was the snake that reached this point. And if it has the same x value as the transformation point, then we can assume that it's above the point. So we finalize with an insertion. Hopefully that makes sense. Let's take a look at the source implementation now. So this is what I was talking about with the 2D array, which contains the furthest x for each diagonal at each depth. Since we're using k as the index into this array, and k can be negative, the middlemost diagonal is now the middlemost element as well. The elements to the left of it would be the negative diagonals, elements to the right of it would be the positive diagonals. So when we access an element in this array, we would have to offset it by max edits, and that's how we get the real index of the k of the diagonal that we are currently inspecting. So the outer for loop here is iterating over each depth. The inner for loop here is iterating over each point on that depth. You'll notice that, okay, we start at the leftmost point and end at the rightmost point. And you'll notice that we are incrementing diagonals by 2, and there's a very simple reason for that. We have these two words. They have 5 diagonals in total. So on depth 0, you'd be on diagonal 0. On depth 1, you'd first start with the leftmost point, which is on diagonal -1. Then you jump over to the next point, diagonal 1. There's no such thing as jumping into diagonal 0 because this would place us in an xy coordinate of 0.5, 0.5. And that's just not a thing. We are incrementing here by discrete numbers. Okay. Go back to screen. Zoom out a little bit. And then here is where we determine whether it originates from an insertion or a deletion, checking the furthest x reached by the surrounding points. And then a bunch of computations. Then we check if it creates a snake. If we do, then we extend that snake as much as possible. We register it in the tracker. And then if we reach the final transformation point, it's fully converted, then we break out of the loop. The next phase of it would be construction, which is the exact same idea. You are iterating over the depths. And now you don't have to check each point. You just have to reverse engineer which x value led to the current depth. So we are referencing the tracker now. And yeah, now we collect all of these edits into a slice of edits, and then that's what we return from the function. So there'd be a type differ here that returns a slice of edits, and an edit would be an edit kind and the associated data with it. That's it for the algorithm diff. There's not much to it. It's only 152 lines of code. If you remove all of the shit that I did in the at the start of it and the assertions, it's more like 70 to 100 lines of code. And then going on to line diffs. With line diffs, the idea is that we compress a multi-line string into a single line, representing each unique line in that input with a unique Unicode point. So we create two maps here, one that maps the line to a rune and then one that maps the rune back to the line. We create a new string for that, and that's what we pass to our character-based algorithm. What this does is now we can reuse the character-based algorithm to create line-based diffs. And then after that, we just convert back the string into the lines that they represent. Here you are mapping back the rune to the unique line that they represent, and then printing it out to stdout. Then for optimized diffs, for the simple heuristics that I mentioned from Neil Fraser's blog, where is it? Optimized. The idea of this is straightforward. I'll just draw it on the whiteboard. The idea behind Neil Fraser's simple heuristics is that you avoid the algorithm as much as possible. You delay using it. So the first step is figuring out the common prefix and suffix of the two strings. So that would be your retain operation. So now you only have to worry about the string in the middle. Second phase of it, okay, let me face it to you. Second phase of it would be, now you have these two strings that have no common suffix or prefixes. Now you want to find if they have a common substring. Now this is the slowest part of the algorithm because this is O of n squared, I think. Yeah. But there is a caveat here. We are only looking for a common substring that is at least half the length of the shorter, or no, half the length of the longer string here. Okay. So if there is, then we know that the two ends of these two strings are conflicting, and that's where we will apply the algorithm. So to summarize, you'd find the common prefix and suffix of the string, and then the middle string resulting from that, you'd find the common substrings between these two. If there is, then on the ends of both of those strings would be conflicting. Now you'd apply the Myers diff for the prefix and the suffix, and you would have it would result in a retain with a Myers diff, and then another retain, and then a Myers diff, and then another retain, and you would do this recursively. If there is no substring, it's just this, then we apply Myers diff directly to the string. So that's the base case right there. Yeah, that's it. Okay, Firefox. To summarize, this is a case study on TigerBeetle. Although I didn't really discuss them much, this is heavily inspired from their testing practices. Snapshot use case is for focusing on the final output. Snapshot implementation, you just replace a string within the source code. Myers diff theory, it's based on the shortest path algorithm with best first search. Implementation, you track the furthest x at each depth, and then you construct the shortest path by deducing the path from the trace. The result of this is that snapshot testing streamlines unit testing. In terms of creation, now you auto-generate the test output. In terms of verification, you take advantage of human-readable serialization or representations to quickly identify the correctness of the output based on the source code alone. This also helps debugging in that we are consolidating on this one representation of the output. Line diffs also pinpoint the mismatch exactly when a test fails. What's out of scope is introspection and coverage. Snapshot testing doesn't help you inspect the object in memory. For example, doing deeper analysis on the fields and the properties that hold between them. And then coverage. Snapshot testing doesn't help you improve your test coverage. You need another testing methodology for that, technique for that. And this is where my library comes in, Golang Snacks invariant. So this isn't a deep dive. I'm just shouting out my library here, and I'll showcase it. Let's say I have a very special case here where if key is equal to ARST, then the world would explode. If we run the tests, count equals 1 to remove the cache, it will pass because we're not testing this. This is not covered in the unit tests. So I'd add invariant that sometimes here, true, ARC would explode the world. Now if I run the unit tests, it'll say that one of the sometimes assertions were never evaluated in the test run. So we would add this in our unit tests. Something simple here. Bool, okay, ARST, true. There you go. So now the test would fail because the world exploded, but you get the idea. Libraries like this help improve your coverage metrics in a way that line coverage would never do, and is something that is out of scope for snapshot testing. I discussed this in one of my other videos called implementation driven testing. You can watch that. And that's the end.